Welcome, future mathematicians! Today, we're diving into a beautiful and powerful tool, the Squeeze Theorem, or as it's elegantly called in French, le théorème des gendarmes, the police officer's theorem. Imagine you have a function that's acting wild, oscillating back and forth forever. Standard limit calculations just leave you stuck with indeterminate forms. The elegant solution? If we can't calculate a function's limit directly, we trap it between two well-behaved functions that we can calculate. It's like having two police officers escorting a suspect. If both officers are heading to the same station, the suspect has no choice but to go there too. This theorem is a game changer for handling those tricky expressions that just won't settle down. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Before we master the Squeeze Theorem, let's do a quick recall of the landscape of limits. Think of limits as describing the end-of-the-road behavior of a curve. 1. Finite at infinity. The curve levels out toward a horizontal line L. 2. Infinite at infinity. The curve escapes upwards or downwards forever. 3. Limit at a specific point. As x approaches a coordinate A, the function might shoot up toward a vertical wall. But here is the big question. What if the curve never settles? What if it just oscillates like a frantic wave? That is exactly where our new tool shines. Let's get into the core concept, bounding a function. Imagine your mysterious function f of x is permanently trapped between a floor function g of x and a ceiling function h of x. We write this as g of x is less than or equal to f of x is less than or equal to h of x. If that floor and ceiling eventually meet at the exact same height, the trapped function f of x has absolutely no choice but to join them at that point. It's perfectly squeezed. Think of it as being escorted by two gendarmes. Wherever they go, the suspect in the middle must follow. This intuitive idea is the foundation of the entire theorem. Here is the formal statement, broken down into 3 logical steps. Step 1, the frame. We must establish that f of x is bounded between g of x and h of x near our point of study. Step 2, the convergence. We prove that the outer bounds, our floor and ceiling, both converge perfectly to the same real number L. Step 3, the unavoidable conclusion. Because f of x is trapped and the trap is closing at height L, the limit of f of x is forced to be exactly L. It's mathematically inevitable. Let's look at this graphically to really see the magic. Look at the black oscillating line, f of x. It's bouncing up and down, making it impossible to find a limit just by looking at it. But notice the green superior, upper bound, h of x, and the red inferior, lower bound, g of x. As we move to the right toward infinity, the green and red curves are crushing the amplitude of the oscillations. They are squeezing f of x tighter and tighter until it has nowhere else to go but toward that dashed line, L. This visual crush is the essence of the Squeeze Theorem. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. To master any limit problem, follow this 4-step master method. 1. Spot the oscillation. Look for troublemakers like cosine, sine, or -1 to the power of n. 2. Frame the bounded part. Use what you know, like -1 is less than or equal to sine of something is greater than or equal to 1. 3. Transform the frame. Multiply or divide the whole inequality to recreate your target function, but be careful with signs. 4. Calculate and conclude. Find the limits of your new floor and ceiling. If they are identical, you've officially used the Squeeze Theorem to find your answer. The problem. We need to determine the limit of the function f of x equals cosine of x over x as x approaches positive infinity. Steps 1 and 2 start with known oscillations. First, let's think about the behavior of the cosine function. As x moves toward infinity, the cosine function doesn't settle on one value. It just keeps waving back and forth. However, it has a very important property. It is bounded. For any value of x in the real numbers, cosine of x is always stuck between -1 and 1. We write this as -1 is less than or equal to cosine of x, which is less than or equal to 1. This inequality is the foundation of our sandwich. Step 3. Transform to match the function. Our goal is to make the middle part of our inequality look exactly like the function we are investigating. To do that, we divide all three parts of the inequality by x. Since we're looking at the limit as x goes to positive infinity, we're dealing with values where x is positive. X is greater than 0. This is a crucial detail because when we divide by a positive number, the direction of the inequality signs stays the same. Now we have -1 over x is less than or equal to cosine of x over x, which is less than or equal to 1 over x. Step 4. Calculate the bounding limits. Now let's look at what happens to the outside functions, the bread of our sandwich, as x gets incredibly large. As x goes to infinity, the fraction -1 over x gets closer and closer to 0. Similarly, as x goes to infinity, the fraction 1 over x also gets closer and closer to 0. Both the lower bound and the upper bound are converging to the exact same value, 0. Conclusion: the squeeze. Because our function is trapped right in the middle of these two bounds, and both bounds are heading towards 0, our function has absolutely nowhere else to go. It gets squeezed into being 0 as well. Therefore, by the squeeze theorem, we can conclude that the limit as x approaches positive infinity of cosine of x over x is 0. Fantastic job! You've just used logic to find order in the middle of infinite oscillations. Keep that mathematical curiosity growing. You're doing great!
Ready for an advanced challenge? Let's find the limit of x plus sine x divided by 2x minus 1. The setup is the same. Start with -1 less than or equal to sine x less than or equal to 1, and add x to all parts to get x minus 1 less than or equal to x plus sine x less than or equal to x plus 1. Now for the trap, division. For large x, the denominator, 2x minus 1, is positive, so the inequality stays the same. To find the limits of our bounds, we look at the highest degree terms. X minus 1 divided by 2x minus 1 simplifies toward 1/2, and x plus 1 divided by 2x minus 1 also simplifies toward 1/2. Since both bounds converge to 1/2, the squeeze theorem tells us the final limit is 1/2.
Sometimes there's a shortcut using absolute values. Let's show that the limit as x goes to 0 of x squared sine of 1 over x is 0. As x approaches 0, the 1 over x inside the sine causes violent, rapid oscillation. Instead of a full floor and ceiling, we can use the absolute value. F of x is equal to x squared absolute value of sine of 1 over x. Since the absolute value of sine is always less than or equal to 1, we get f of x less than or equal to x squared times 1. We know that as x goes to 0, x squared also goes to 0. By the squeeze theorem, the null limit case, if the absolute distance to 0 is squeezed to 0, then f of x itself must go to 0. It's a quick and elegant way to prove convergence. To be a math pro, you must avoid these fatal errors. Error 1 is the sign trap. If you divide by a negative number and forget to flip your inequality signs, changing less than or equal to greater than or equal to, your logic breaks. Error 2 is the split limit. If your floor goes to 2, but your ceiling goes to 5, you haven't squeezed anything. The theorem simply fails here because there's too much room for the function to wiggle. No conclusion is possible unless the bounds are strictly identical. Always check these checkpoints before finalizing your answer. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Which tool should you use? Here's your decision matrix. If your expression oscillates, sine, cosine, power of n, the squeeze theorem is your best friend. If you have a standard indeterminate form, like 0 over 0, use algebraic techniques. For fractions involving powers, logs, or exponentials, use comparing growth rates. If you just need to show a limit goes to infinity, use a single lower bound. And for simple algebra with no oscillations, just perform standard operations on limits. Picking the right tool is half the battle. Presentation matters. Here's how to write a perfect exam response, standard exam-style writing. Start by stating your interval for all x greater than or equal to 1. Next, show your bounding step. -1 is less than or equal to cosine x, which is less than or equal to 1. Therefore, -1 over x is less than or equal to cosine x over x, which is less than or equal to 1 over x. Then, show that you calculated the limits of the bounds. Now, the limit of -1 over x is 0, and the limit of 1 over x is 0. Finally, state the theorem to conclude. According to the squeeze theorem, the limit of cosine x over x is 0. Following this clear and logical structure will help you earn full marks and impress your grader. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Try it yourself. Prove mathematically that the limit as x approaches 0 of x times cosine of 1 over x equals 0. Your toolkit. Identify the oscillating part. Remember the absolute value shortcut. Construct your frame carefully. Here is the detailed correction for the Try It Yourself challenge. Step 1, we bound the oscillator. For all x not equal to 0, -1 is less than or equal to cosine of 1 over x is less than or equal to 1, which means absolute value of cosine of 1 over x is less than or equal to 1. Step 2, transform by multiplying by absolute value of x. This gives us absolute value of x cosine of 1 over x is less than or equal to absolute value of x, which translates to the frame negative absolute value of x is less than or equal to x cosine of 1 over x is less than or equal to absolute value of x. Step 3, now we look at the limits. Both negative absolute value of x and absolute value of x approach 0 as x goes to 0. Conclusion, by the squeeze theorem, the limit of x cosine of 1 over x as x approaches 0 is exactly 0. You did it! You've mastered the art of taming wild functions.